Thank you. Can you guys see the slides?
Yes.
Okay.
Yes. Perfect.
So thanks for having me. So I'm going to talk about robot navigation in real world and kind of some methods that can kind of get us where scaling up navigation. So service robots, where robots we can plug them in the environment, they can do something useful, go from point A to B and handle whatever is happening in the environment, have potential to be really impactful, right? So what we need for that, we need robots basically to handle the real world. And this is an example where we have robot trying to get to the sink in this environment and just dealing with whatever is happening in the scene. And over several runs, environment changes because people are there. We did not stage this. Here is a janitor coming in. And we need methods that can do this. This is reinforcement learning policy, fully trained and in simulation and just running on the robot. The robot receives relative pose where it needs to go, so the goal condition policy, and observes sensors and moves and outputs the velocity and linear and angular velocity. So that's the real world. On the other hand, we also need to have these methods work on real robots. And that means that each robot, what they can see, what their dynamics is, what are their shapes, and even really onboard compute determines what they can really do, what are their inherent abilities. So the way fetch robot and a little legged locomotion robot, the motion will be very different. This can crawl under tables, this one cannot. Even these two robots that have the exact same hardware, there is 100 pounds difference in weight and even height and so on. So we need to have a set of methods that works for any robot to be able to do safe and feasible motion with respect to that particular robot in dynamic world. So there are two questions that I'm going to address here. First is how to train static obstacle avoidance in real world. So this would be your goal condition policies that transfer between the environments. And robot does not need to know where and how it got to the environment, just needs to go and execute what it needs to do. There are many ways to do this. There's a big question whether to train directly from the from the real data. In this use cases with the navigation, it is very difficult to train from real data because there's a safety concerns and so on. Another option is to get some imitation data, which possibly might not scale. But I'm going to focus here on training these in simulation, and then we need to address the sim to real gap. And then the second part, I'm going to talk about how to adapt this to the dynamic environments. So this is reinforcement policy, as I said. The observations are noisy LiDAR observations. We'll look 3 of them just to have a little bit of the history and estimates of the robot's velocities. As I mentioned, the actions are linear and angular velocities of the robot. We train in a very simple static environment. And the objective is to reach the goal. The problem with this is that this reward is static, sparse, and it's not susceptible to training. So the question is how to select a reward that can serve as an intrinsic motivation for the agent and propel the learning. Second question we need to answer is how to select the neural network architecture in this case, how wide and so on the policy is. And third question is how to create a simulator that can actually facilitate zero shot sim to real gap. And most of the time this is done by trial and error, and that's very painful and not the best way to do it. So one way is to automate the process and start a population of reinforcement learning agent we have good intuition about what that intrinsic reward might be. We know that it might depend on how far from the wall it is, what is the distance to the goal, what is the orientation or speed of the robot, but how these kind of pieces fit together, that's the parameterization, right? And that's the part that we can mutate. So we start with kind of randomly parameterized rewards, train each agent, observe how they perform with respect to the task objective, which is whether it reached the goal or not. And then based on these information, do basically propose the next reward and kind of keep that process for a while until we get a good reward policy that makes learning tractable. And then on the next step, we basically repeat the whole process. Now that we have a reward fixed, we can then basically do the same thing with the neural network architecture. We can vary the size of and the number of layers in the network, evaluate how it performs, except that in this case, we're evaluating over the reward. And we get then the neural network architecture and the policy that performs well. So that kind of yields the algorithm for training these policies. The simulator is super simple, like here. When we're training the policies, the simulator produces the main randomization with the noisy sensors and actuators and a kinematic model. And we randomize initial and goal conditions. And these two first pieces are important for the resilient policies that are able to do sim to real gap or bridge it. And then when we're training, we do this out-RL business that I just described. We learn the rewards in neural network architecture, and that step produces competency. The policies are competent and result in being good agents. We do zero-shot transfer to even environments with the dynamic obstacles, and it generalizes to unseen environments and adapts to the changes on the go. The reason it adapts to the changes on the go because it's a reinforcement learning. It observes, it sees where it is. Next step, if the obstacle moved a little bit, well, that's kind of part of the noise of the environment and just kind of goes on with that. And the same process works on a bunch of other robots, including those with the kinodynamic constraints. So something that has very complicated or difficult dynamics like asteroid robots, reinforcement learning using this method can produce reasonably well point-to-point policies. How about if we now have something like a nanodrone that has few kilobytes available RAM, very small, light, and cheap? How do we train these policies on the robots? The compute does matter because this little nanodrone has Raspberry Pi, or very kind of cheap processor on it. And it's not reasonable. We cannot train policies on that processor. We train on the GPUs and high-end hardware. Why do we expect that if we train on the high-end hardware and then plop the policy onto Raspberry Pi that is going to work? And it's not. You see here on the left side that there is actually a big gap between the trajectories of the two. And what do we do about that? So this is another source of the sim to real gap that's kind of often overlooked. It is the difference between the compute. We know about the sensors, we know about the dynamics and so on, but actually the fact that we're training on one system and doing inference and running on the other actually causes. So one way to go about that is to, we use the technique that's called hardware in the loop. It's from the system architecture community. Basically, the simulator allows us to plop in or plug in the target compute. And that way we can run the policies. We can run the simulator on the desktop. We can run our train agent on the target hardware without running it actually on the UAV. Goes to the flight deck and then shows it back on the simulator. So it really mimics how the UAV would fly without actually flying and without damaging the hardware and so on. And what we can do with that then is to actually see the latencies and measure the latencies between the target hardware and the one that we're using for training. So for example, inference latency on the Raspberry Pi is 68 milliseconds, while on Intel Core is 3 milliseconds. We can use that and kind of plop it in the simulator, and then even though we're training on GPU in simulation clock time, we can simulate the latencies and actually get to the policies that are bridging that sim to real gap that's due to the compute. So let's see, doing something useful for that. This was just presented yesterday at ICRA. It's a source finding. So training, want to train the nano drone to find the light. And there are two steps. We use the air learning simulator, and we equip it with a light model where we observe the actual light source in the environment and fit a Gaussian process to simulate the light. And then again, we do domain randomization for the training process. And then to design the system, because this policy really needs to be compact and fit the memory, we can't use like an image or whatnot, just use very sparse reading, 4 laser readings for the distance and 1 for the light sensor as an input to the network. And that's our basically the neural network architecture and the POM-MDP for the agent. And we train that, and we actually have the autonomous system that can, with a 80% success rate, find the light source. And it does pretty well. It gets confused in the darker spaces, but then once it gets to the light, it finds and kind of proceeds towards the goal. So to train in the static obstacle avoidance in the real world, proposing here to train in simulation and address all sources of the sim to real gap, including the compute, and then automating the hyperparameter search with the evolution to get better competency of the policies. And then domain randomization provides the resilience. That said, these policies are never going to be perfect. And there are limits to that, especially in the dynamic environments. The reason why they're even adapting a little bit is because they have some noise tolerance. But beyond certain points, if the obstacles are fast and so on, we need to have a higher level policy that says, hey, go left or right to from the obstacle. So now I'm going to mention 2 methods for dynamic environment for navigation in dynamic environments. One is on the obstacle avoidance, and the other one is on the cooperative tasks. So in this here, we want to have a visual navigation around humans. So basically with the same thing that we had there, previously, but we're using camera instead of the LiDAR, and we want to basically navigate around the humans in not known, a priori unknown environment. There are several challenges with that. One is the photorealism, and bridging the sim to real gap in visual environments is much harder than LiDAR-based environments. Second challenge is safety. Training around humans, there is a cause of or risk of damage and injury and so on. And then the third one is really creating a data set. There are concerns with the privacy and diversity of the human data set, how we do representation and so on. And these are hard challenges, right? So how do we go about addressing them? In simulation. Basically, we already have at our disposal models of humans. This is a real data set. And we also have scans of the building environments, 3D indoor. And we can superimpose these 2 data sets and create a simulator that is programmable. In addition, for the humans, we can also change the parameters and be able to identify things like gender, texture, which is clothing, skin color, facial features, body shape, and motion, and have this simulator that is parameterized and basically just change the parameters and have very different diversity or however we want distribution of the environments and the humans in it. And that's something that is not easily done from gathering the data or imitation learning and so on. It would need prohibitively many data samples and whatnot. So here is an example of what that environment might look like. Basically, we're just superimposing people, and when they're moving, their legs are kind of more spread out than when they're not, and so on. So how do we use this? The key here is that we want to find a waypoint that this is basically a waypoint selection. If I have a human, I need to decide whether to go to the left or to the right or find a good point to avoid it. Motion has structure in it. The dynamic obstacles, whether they're humans, right, or other agents or physical objects, are subject to physical laws or intents. So there is a structure in that motion. And what we can do now, since we have privileged environment, we can practice in these known environments. We can randomly generate and place humans' initial poses and goals in these buildings. We can let them run, solve the problems with MPC or other method, which requires the knowledge of the human trajectories, which we have in the simulation, find the best or the most optimal waypoint, and then construct a data set out of the initial conditions that says, okay, if I started here and I need to go here and the human is here, then my waypoint should be somewhere around here. And that's a supervised data set. It's a self-supervision. From there, we basically just train the model. And that associates the initial condition with optimally placed waypoint. And then once we have that model, this is the perception module that outputs a waypoint and goes to the planning and trajectory feedback on the robot. It executes, observes, and this is the standard loop. It achieves 80% success rate and higher than the baselines with the zero-shot transfer. And here are some couple kind of analysis on where it's going and how it's going. So in this case, we see this is a human. Dashed line is here when the human is static. It decides to go in front of it. When the human is moving in this direction, it decides to go down the red line. In this case, this is the baseline. Baseline is the dashed line. It decides to go in front of the human and collides, whereas the red line goes behind and avoids the collision. It even has some ability, even though it wasn't explicitly trained, to adapt to multiple humans. So in this case, kind of swirls between them. And here is an example of the zero-shot transfer. Person comes in and it avoids. The baseline would cause a collision at this point. Here's another example. Person comes around the corner and the robot goes around. So the last thing I want to briefly mention is the multi-agent rendezvous task in the mapless navigation. And this is an example of a cooperative task. So in this case, the multi-agent system is inherently dynamic, right? And if these two robots need to do something together, then they need the one needs to adapt to the changes of the other one. So in this setup, we assume that we don't know where they need to meet or when, and they need to kind of figure that out. And that each one of them has noisy sensory information and its own mapless point-to-point policy, like we talked in the first part of the talk. And they are planning decentralized, so they're not communicating, they just share the objective. And the idea is to have this to generalize to new environments with the obstacles. So to go about that, it would be really good if a robot had a model of itself and its teammates' behavior, because assumption here is that neither the robot nor its teammates are behaving perfectly, nor we know how they're behaving, right? So if we had the model, then we can do planning on top of the model. So can we learn the model? That's exactly what we're doing. And basically it's the same self-supervised idea that we can practice behaviors. We can basically open the simulation environment, plop the robots, let them run their policies, observe each other, how they move, and say, hey, okay, so if I know that it received there, this is my goal. Given that goal, in time delta t, given this initial position and my sensors, I can predict where they're going to be. And that creates that creates a data set that we can then train the predictive model that predicts robots' own behavior and the teammates. And we see the learning curves, they're both converging, and self-prediction is better, which kind of makes sense because we have our own sensors, and the prediction of the other agents is slightly worse because, well, sometimes they're occluded and whatnot. It's within the obstacles. So once we have that, then they plan together. And the idea is that each robot then goes, basically we're using the cross-entropy model-based RL to find the point in the middle and sample around these points, roll out the predictive models and see what the future might look like. And in like this case, this is not feasible, goes and then proposes the next point and so on. And we close and narrow the search region until we select a waypoint and they move and we move forward and so on. So between the baselines, this method actually, we are the blue line and centralized is the yellow. In terms of how closely the robots end up together, we're pretty close to centralized without actually having, being decentralized without having any knowledge about what the other agent is going to do, nor having assumptions of its own policies. And here is a video. And this is due to COVID in simulation. We also had the on-robot experiments. They're meeting here. The centralized baseline kind of goes in this local minima where they're close to each other, but they're really not stopping. the classic RRT, it's kind of getting there. Similar to this environment, the hierarchical planning meets together, whereas the centralized ends up in this kind of weird local minima where they're chasing each other. So, oops, next. Okay, so for dynamic obstacles, we talked about two tasks, avoidance and cooperation tasks. And the key idea here is that there is predictable motion, that we can observe, learn, and use these predictable motion models in new environments, and that the self-supervision and planning bring resiliency and competency to the policies. So higher kind of themes and reflections is the training environment, design, and domain randomization across different dimensions close the sim to real gap. That evolution and reinforcement learning leads to better reinforcement learning agents with less engineering, especially when we have the fixed properties of the system. And then that self-supervision with reinforcement learning creates planning that improves with the experience that's within agents' abilities. And it basically creates a planner that is able inherently to deal with the imperfect agents and kind of just adopt to whatever is happening on the scene. And then fourth thing is really we have evolution here, reinforcement and self-supervision working together is three separate methods, and we get better evolution method or better RL algorithm, the whole system is going to improve. So the future work would be really nice to see more about uncertainty and having the guarantees as where this noise and so on is becoming enough and where things break down and so on. And then the second line is that seems like that the environment design is inherent to the training these policies. So more work on, and work on looking into that on co-training environments and the agents together and creating the system that to kind of remove this additional or hand designing the sim to real gap pieces. And with that, I want to thank the collaborators, and here's the list of the papers, and I guess we'll leave the questions for later.